Okay, so let's talk some buckling. So I'm going to use a wooden column here, a wooden support column. Uh, it's got a Young's modulus of 1.6 times 10 to the 6 psi. It's going to be 10 feet long. I'm going to fix it at the bottom, so no rotation allowed at the bottom. I don't know, maybe set it into the concrete or something like that that does it. And then at the top, it's going to be pinned. So it's going to be pinned in a manner that it can rotate about the z-axis, but can't rotate about the x-axis. So again, based upon, this coordinate system right here, x is in this direction, z's in this direction, y is the vertical. And then my coordinates, x is this way, z is this way for the cross section. So the 4 inches is the z the x direction. The 2 inches is the z direction measurement. And so basically, and here's kind of like a view kind of at the pin. So again, we can rotate. The pin's parallel to the z-axis, so it's able to rotate about the z-axis without any problems. So yeah, I just rewrote our. Oh, I forgot the squared there. Rewrote our beam buckling formula. So pi squared EI over KL squared. Well, the KL squared. Where KL is basically the effective length. It's based upon the buckling mode. So we got two buckling modes that we can talk about. We have the one where it's buckling by rotating about the z-axis. So that'll allow free rotation here at the top. It'll still be fixed at the bottom. Based upon that, our effective length is 1.7 L. Whereas if it's buckling about the x-axis, then it's not free to rotate at the top because it's kind of, the pin's what allows it to rotate. Only the pin allows it to rotate about the z-axis. It can't rotate about the x-axis. So effectively, if we're looking at it for about the x-axis, it's fixed. So there, our effective length is 0.5 L. So again, if we're rotating about the z-axis, our effective length is 0.75 times RL. But our I needs to be calculated based upon rotation about the z-axis. So again, just a reminder, x-axis this way, z-axis this way. So that's 4 inches, and that's 2 inches there. So our I calculation for about the z-axis. Come on, let me erase. There we go. Our I calculation about the z-axis, that's going to be 4 inches cubed times 2 inches divided by 12. That gives us 10.6 inches to the fourth. If we're rotating about the x-axis, however, again, our k is going to be 0.5, but our I needs to be calculated based upon rotation about this axis, which again is going to be substantially easier than rotating about this axis. So our I there is going to be 2 inches cubed times 4 inches divided by 12, which gives us 2.6666666 inches to the fourth. So plugging in the numbers, we got our pi squared times 1.6 times 10 to the 6 pounds per inch squared times 10.6 inches to the fourth, all divided by our effective length squared. I actually forgot to put the squared sign on my drawing. Sorry, but the calculation had it correct. Anyways, so that's the effective length there, again, it's 10 feet, so 10 feet times 120 inches, times 12 inches per foot gives us 120 inches, times the 0.7 factor gives us 84 inches. So all that on the top divided by 84 inches squared, and all the inches cancel out. We got inches to the fourth here. We got minus 2 down here, so I can cancel out 2 of those, and then inches squared down here too. So all that works out to give us a value of 23.7 kips is what we're gonna be able to see if the only failure mode was rotation about the z-axis. On the x-axis side, however, pi squared times 1.6 times 10 to the 6 pounds per inch squared times our I value, so 2.66 inches to the fourth, all divided by 120 inches by 0.5 squared, so all divided by 60 squared, 60 inches squared. That gives us a value of 11.69 kips. So this is going to be our critical case here, because that's a lower load than what we see over on this side. So we're failing based upon this failure mode here, not this one. And that's just because it's substantially easier to bend a 2x4 about the it's easier to bend it about this axis than it is to bend it about this axis. And that's about that.